Hi everyone. Today I'll talk about the relationship between probabilistic circuits and determinant point processes. I'm Honghua from Computer Science Department of UCLA. Let's start with a motivating example. Suppose we want to recommend products to a customer at a store. We have a green iPhone, a yellow iPhone, an AirPod, and a potato. Given that a customer has just bought a green iPhone, instead of recommending a yellow iPhone or a potato to the customer, we would like to recommend an AirPod. So how can a machine learning model do this? One way to solve this problem is to model the probability distribution. What should we expect from our probabilistic model? There are some questions that we want to answer. For example, what is the probability that a customer buys exactly a green iPhone and an AirPod? That is, we want to evaluate the probability to the following assignment. Or what is the probability that a customer buys a green iPhone and AirPod and possibly other items? That is, we want to compute the following marginal probability. To solve this problem, people have developed tractable probabilistic models, TPMs. TPMs in general should model probability distributions efficiently and answer probabilistic queries efficiently. Various TPMs have been developed for different purposes. Here's part of the landscape. We can see probabilistic circuits, the class of graphical models with bounded tree width, and determinant point processes. Though each of the classes is individually well studied, the relationship between them are less extensively explored. In particular, we noticed that the study on the relationship between PCs and DPPs is completely absent. So what do we know about this relationship? The green circle represents the set of distributions that can be represented by polynomial-sized PCs, and the yellow circle represents the class of DPPs. First of all, we note that PCs can represent positive dependence, which is impossible for DPPs. Both PCs and DPPs can represent the fully factorized distribution. However, we don't know whether the area marked with a question mark is empty or not. That is, we don't know whether there exists a class of DPPs that cannot be represented by polynomial-sized PCs. This is the main question that we're trying to answer, but before that, we first give a short introduction on both models. So let's start with DPPs. Here, defining matrix L, indexed by the items given in the motivating example. Along with that, we define the probability distribution such that the probability of a subset is proportional to the determinant of the submatrix indexed by the elements in the set. For example, the probability of the set the green iPhone and an AirPod is given by the determinant of the submatrix colored green. Here, this probability distribution is a DPP. DPPs are tractable in the sense that probabilities normalizing constant marginals can be computed in polynomial time. Now let's look at probabilistic circuits, PCs. This figure defines the probability distribution over the four items. To evaluate the probability, we set the values of the leaf variables properly and propagate the values upward. For each sum node, we take a weighted sum over its children, and for each product node, we take the product over its children. The probability of the assignment is simply proportional to the output of the circuit. Note that PCs seem to be very general, so it brings up the question, why are PCs tractable? In general, inference tasks such as computing the marginals are intractable for PCs. To guarantee tractable inference, we need to assume some structural properties. For example, something called decomposability allow us to compute the normalizing constant and marginals efficiently. A property called determinism, together with decomposability, allow us to compute allow us to do map inference efficiently. Given these structural properties, people have identified several subclasses of PCs. For example, a decomposable PC with non-negative parameters is called a sumproduct network, an SPN. Probabilistic sentential decision diagrams, PSCDs, are deterministic and decomposable PCs with additional structural assumptions. All right, let's get back to our original question. How can we represent DPPs with polynomial-sized PCs? In particular, we also want structural properties of the representation to achieve tractability. Our first observation is that this question may be answered by a two-step solution. Step one is to represent the operation of extracting submatrices as a PC, and step two is to represent the computation of determinants as a PC. To solve step one, we propose something called symbolic kernel. So given the DPP kernel L, we construct a symbolic kernel lstar, which effectively captures the operation of taking submatrices as a PC. However, step 2 is not easy. That is, representing the computation of determinants as a PC is hard. Converting the known algorithms to a PC is not immediate. Gaussian elimination, for example, requires division and branching, and Laplace expansion requires the computation of exponentially many subdeterminants. Moreover, and more importantly, they don't give us the properties we want. All right, so we, after several unsuccessful attempts, we started thinking that we might not be able to represent DPPs by polynomial-sized PCs with structural properties. Turns out that we were right. We illustrate our results as a roadmap here. So you can see an axis. We will fill it in with different classes of PCs. From left to right, the structural assumption on the PCs gets weaker and allows for greater expressive efficiency. At the same time, from right to left, the tractability of PC gets stronger. Now let's start with PSTDs. So they are deterministic and decomposable with additional structural properties. Can we represent DPPs with PSTDs? No. Similarly, the answer is still no for deterministic PCs and deterministic and decomposable PCs. Now, what if we drop decomposability? Can we represent DPPs with deterministic PCs with no negative parameters? Unfortunately, the answer is still no. What if we drop the constraint that the parameters are non-negative? The answer is still no. Now let's go back and drop determinism. Can we represent DPPs with decomposable PCs with no negative parameters, namely SPNs? The answer remains to be no. What if we drop the assumption that the parameters has to be non-negative? We don't know the answer yet, so it's still an open problem. Here are the formal statements of the negative results that we proved on the. And now let's conclude with some perspectives. We've proposed several open problems. The first one was already mentioned before. That is, can we represent DPPs in general by polynomial-sized decomposable PCs with negative parameters? The second one is slightly trickier. That is, can we represent L ensembles in general by polynomial-sized decomposable PCs? The subclass of DPPs that we constructed that cannot be represented by decomposable PCs are not L ensembles, which are a subclass of DPPs that is commonly used in practice. So problem number 2 still remains open. All right, so conclusion. What did we do in this project? So we started a systematic study of the relationship between PCs and DPPs. We proposed symbolic kernel as a mean to unify PCs and DPPs. We proved 3 negative results on the problem of representing DPPs as PCs. And we proposed several open problems and motivated the study of the relationship between different TPMs. All right, that's basically it for the talk. Thank you for joining. Feel free to contact me if you have any questions.